Okay, so let's talk a little bit about filter design. And we're going to talk about finite impulse response filter design. And the basic idea here is that you want to pick a frequency characteristic that you want, and you perform an inverse Fourier transform. Why? Because remember, filtering is applied in the time domain. So what we really want is a filter that has these coefficients or elements of the array that are equal to the time domain signal of the frequency domain that we specify. So we only need the magnitude spectrum because in an FIR filter, they have linear phase. So the phase is uniquely determined by the magnitude spectrum. Another big advantage of using FIR filters. Now, as a general rule, you would want the sharpest boundary possible between the pass band and the stop band. So here's an example of that where we have some filter that basically has an infinitely steep slope at minus pi over 2 from minus pi to minus pi over 2. So we turn on here at minus pi over 2, turn off at pi over 2. So if we have the, if we define this as just a rectangle running from minus pi over 2 to pi over 2, then the inverse FFT will give us the impulse response of the ideal filter. So a couple of things. First of all, you're referencing your frequency from minus pi to pi because that's just the way MATLAB is going to implement this. So to convert to the time domain, we're going to take the inverse Fourier transform of this rectangular window function. Now the frequency's in radians, so this would be our rectangular window. Because the frequency's in radians, instead of that 2 pi nf that showed up in previous chapters, 2 pi is contained within omega, so omega is 2 pi f. So we switch the n index to k, and we just have e to the j k omega. And then we're going to take the inverse transform of that to get the coefficients in the time domain. When we do that, we get the following function. We integrate that from minus omega c to omega c. We get this, we put in the limits, and we get this function right here. Okay, so let's look at the next slide, and let me go back. Note that this n is a typo in the textbook and should actually be a k. Okay, so going to the next slide, you see this term is actually the sine function. And so if we replace, it's Euler's relationship for sine. So if we replace this with the sine of k omega c, then our rectangular window looks like the following. It'll be the sine of k omega c over pi times k. This is referred to as the sinc function. It's sine of x over x. The cutoff frequencies of the filter are relative to the sampling frequency. And so in MATLAB, it actually takes Nyquist into criteria. So your actual cutoff frequency is your cutoff frequency divided by 2 times the sampling frequency. So for rectangular window filter design, when k gets very small, the sine of 0 is 0, so we would have 0 over 0. But the sine of 0 can actually, when theta gets very small, the sine of theta is approximately theta. So if we replace the sine of theta with theta in the limit, we get the following expression. The k's cancel. And so your initial component, your 0th component of your filter is basically 2 times the cutoff frequency. So when we then substitute for omega, we get that b sub 0 is omega c over pi. So here's what the impulse response of a rectangular window filter looks like. Sine of x over x. We can define different filter lengths. The cutoff frequencies shown are relative to the sampling frequency. So here's a cutoff frequency of 0.1. Here's a cutoff frequency of 0.4. So your cutoff frequency is relative to a maximum frequency of pi. And if you then want to convert that to hertz, you have to remember that the maximum frequency in the spectrum of a sampled signal is the sampling frequency. But then typically you want to obey the Nyquist criteria. So you want to define your sampling frequency as sampling frequency over 2, the Nyquist criteria. So the cutoff frequency is relative to the sampling frequency, and the actual frequency then is cutoff over sampling. So if you want to know based on Nyquist your actual frequency, it's the cutoff over 2 times the sampling frequency. All the MATLAB design routines take Nyquist criteria into consideration. So let's look at an example. Let's use a Fourier transform to find the magnitude spectrum of a rectangular window filter for 2 different lengths, one length of 18, one length of 66. And we want to use a cutoff frequency of 300 Hz. We have a sampling frequency of 1 kHz. So our relative frequency is 0.3. So first we're going to generate the filter's impulse response using the rectangular window equation. And since L is even, then we have to round up to produce 19 and 67 coefficients because the filter has to be uniform about center. So the filter will have to have an odd number of components. So after we calculate the impulse response, we're then going to find the spectrum by taking the Fourier transform, and we're going to plot the magnitude. So ideally, when we do this, we're going to expect a rectangle because we've designed it in the time domain. We've designed its impulse response, designed it in the time domain, so we've used the sinc function to do that. So then when we transform the sinc function, we expect a rectangular function. So here is the program. We're just looking at 2 different potential filter lengths, 18 and 66. We're going to put a for loop so that we evaluate each length. Here are our filter coefficients, sine of 2 pi of ck over pi k. Now then, we then flip left and right, and the reason that you're doing that is, remember, you are convolving in order to filter. So what the flip does is the flip is going to then give you all of your BKs as positive values. Then we're going to do the FFT and take a subplot, take the absolute value, etc. And so here's what that looks like. For the 17 element filter, you can see that there's quite a bit of ripple, and you can also see that this is not an infinite slope, it is a finite slope. As we increase the length, the ripple remains at an increased frequency. The slope gets steeper. We also have these oscillations that show up above cutoff. So this is referred to as the Gibbs oscillation, and it happens because we basically truncate that infinite impulse response. In other words, our filter has a finite length. It doesn't go from negative infinity to infinity on our sinc function. Because of that, we're going to get ripple. In this case, we're getting ripple in the frequency domain. So the Gibbs oscillation is what that is referred to. They're due to truncating an infinite function. And so one way to reduce those is to go with a window so that you don't have that rectangular windowing that truncates that function. And so repeated again here are the Hamming window and the Blackman-Harris window with typical coefficients. So we can apply a Blackman-Harris window to that rectangular window filter. And then in this case, we're going to calculate and display the magnitude spectrum of those impulse functions after they've been windowed. So everything is pretty much exactly the same right to this point. And now what we're going to do is we're going to define a window length to be the same length as the filter. We're going to create a vector from that, and then we're going to generate the Blackman-Harris window for that particular length. Then we're going to take our filter coefficients and multiply term by term by the Blackman-Harris window, and that's why you have this dot asterisk here, because you're multiplying term by term. Otherwise, MATLAB will try to default and do a vector multiplication. We're then going to take the FFT of the newly windowed filter function. And so what you see is for the Blackman-Harris, you see for this length of 17, I don't have the other one to compare with, but basically the cutoff is all those oscillations are gone. So you don't have the oscillations here either in the 17 or the 65. The 65 length window has a sharper cutoff as you might expect. The 17 length is a slower, more rounded cutoff. So our 65 element filter is approaching that rectangular window. We still have a finite slope, but it's better. The disadvantage of going with the longer filter is that it does increase your computational time because you are increasing the filter order. Another example, let's apply a low-pass rectangular window filter to a respiration signal. Going to use the Blackman-Harris window in this case, and we want to apply this filter using convolution. So I just want to say here that MATLAB has many toolboxes that avoid having to use convolution. In this case, this is being done in this book so that you see that basically what's hiding behind a lot of the MATLAB toolbox commands is a convolution function. So what you're really doing is you're constructing a filtering system that's similar to what MATLAB already has coded. So yes, we are kind of doing this the long way. So let's see here. First of all, notice he has not coded this time. We have not coded the Blackman window, actually using Blackman, the command to create a Blackman window. So we've already simplified this a little bit. Here's the sync function, and then here's the convolve, the respiration signal with the B, and in this case the same here means that we're looking at a causal filter, and then we'll plot the data. So here's our original signal, and here's the filtered signal, and you can see that a lot of the noise is missing, a lot of the higher frequency noise is missing. It's not so obvious here what's happening on the lower end of the frequency spectrum because in the original signal we're not seeing a lot of DC drift, so that's not really evident that we filtered at the low end of the frequency spectrum, but certainly the filtration at the high end of the frequency spectrum is showing up here. Okay, here are some other FIR filters. Oh, you know what? I think that previous slide, I think that was a low pass, so that would explain why we're not seeing the low end filtering. Here are some other equations for different FIR filters. The high pass filter is shown here. The band pass contains both a high pass and a low pass form, and the band stop basically flips the high pass and low pass so that you have a band stop instead of a band pass. And so these equations will implement the high pass, and band stop filtering respectively. Here's my band pass filter problem. So in this case, we want a lower cutoff frequency of 6 Hertz and an upper cutoff frequency of 12. We want to use the Blackman-Harris window. We want to use 129 coefficients. So in this case, we'll have a high pass part and a low pass part. So we'll have that our B sub 0 is 2 times the high pass cutoff minus 2 times the low pass cutoff. Our sampling frequency is 100 Hertz. So in the code here, you get your high and low pass. Remember, they are relative to the sampling. So we take our 12 Hertz and we divide by 1,000. Or 100, we take our 6 Hertz and we divide by 100 so that we're getting those fractional cutoff frequencies. Very important to do that. Then we construct our array so that we can get the negative components of the filter, because remember the filter's centered around 0. We then do the flip left to right. And then the multiplication of the Blackman times the filter coefficients, and then finally the convolution of the EEG signal and the filter, and then the terms same, so that we know that we're applying a causal filter. So a bandpass filter that's produced by those coefficients in conjunction with a Blackman window. Here's an example of one where we use 33 point length filter and 129 point filter, and you can see the difference in how sharp the cutoff is as well as how sharp the attenuation is. Both of these using a Blackman window, so that Gibbs phenomenon is not showing up. We're not seeing a ripple here. So this bandpass filter is then applied to the signal via convolution. Let me come out of the slideshow so that I can try and separate these out a little bit better. Go back to the... So here's the unfiltered signal, and then here's the filtered signal. Now you can see, if you look here, you see we've got a little bit of low frequency kind of signature that's clearly flattened out here when we apply the bandpass filter. So that low kind of drift, low frequency drift that's showing up has been zeroed out. Sometimes it's very dramatic and the whole signal just kind of goes all over the page until you apply that low pass filter. So the bottom line is when we do a filter design, we basically are designing what we want in the frequency domain, but we're actually implementing the filter in the time domain through convolution. So we have to take our frequency domain, take our inverse transform, get a time domain representation of the filter coefficients, and then implement those via convolution.